Hi and welcome to this sixth lecture in this course on reinforcement learning. My name is Hado van Hasselt and today I will be talking to you about model-free control. The background material for this lecture is chapter 6 from Sarsa and Barto. You might recall from the previous lecture that I said there were a bunch of chapters background material, 5, 6, 7, 9, 12. But this lecture specifically will be focusing mostly on the contents of this one chapter 6. Just to recap, again, here's the interaction loop of an agent interacting with the environment, and then reinforcement learning can be taken to be the science of learning how to make decisions. And the agent can internally learn a policy, a value function, and/or a model. This lecture we'll be focusing on value functions again, like last lecture. In the last lecture we were focusing on predicting value functions, and now we're going to focus on additionally using those value functions to then come up with a policy. We won't yet talk about models. This general problem involves taking into account time and consequences, so we have to make predictions about long-term futures because actions cannot just influence just the reward, but also the agent state and the environment state. And this means that actions can have long-term consequences. Now, in the previous lecture, as I mentioned, we covered model-free prediction, which is all about estimating a value function in an unknown Markov decision process. So we imagine there's some reward. For instance, this could be taken part of the observation, or this could be taken as part of the agent where the agent has a certain preference over different observations. And then value functions are defined as the expectation of the accumulation of these rewards, and that's what we try to optimize. But in the previous lecture, we didn't talk about optimizing those, we just talked about predicting them, and then this lecture is about model-free control, in which we will try to optimize these value functions. The first topic that we'll touch upon is Monte Carlo control. So before introducing Monte Carlo algorithms, I'm first going to recap policy iteration. So policy iteration was described in the lectures on dynamic programming taught by Diana. And just to remind you, policy iteration refers to interleaving two separate steps, which are called policy evaluation and policy improvement. And that's depicted here on the left, where we start with some arbitrary initial value function, for instance they could all be zeros, and some arbitrary policy, for instance uniformly random. And then the first step could be to evaluate this policy. So we depict it here with this arrow going up, and then when we reach this line, that means that the value function is now fully accurate for the value of that policy, the actual value of that policy. That will be the policy evaluation phase. Then when we've reached this value function, we can do a policy improvement step. For instance, we can make the policy greedy. And this policy improvement step will change the policy in such a way that we get a new policy, pi prime, such that the value of that policy in every state is at least as high as the value of the policy that we were just evaluating. And picking a greedy policy is one way to achieve this. But because we're changing the policy, that means that our value function will become inaccurate because it's an evaluation of the previous policy, but we've now changed our policy, which means we can do the evaluation phase again for this new policy and again find the true values for that policy. And then because the value function has changed, greedifying the policy with respect to that new value might also change the policy, and so on and so on. We see that depicted here as well, where these arrows mean that we're basically overwriting. So first we start with some policy, let's say random. We evaluate that policy that gives us a value function. Then we consider a new policy, which for instance picks the greedy action in every state. And then we can do the evaluation again, and so on and so on. When this ceases to change anything, that means that by definition we must have found the optimal value function, because it means that the true value of the policy is equal to when you then consider the greedy value. And that by definition will be the optimal value function. So this has all been discussed in lectures 3 and 4. We're going to use this as an intuition to build model-free algorithms, because before with dynamic programming, for instance the policy evaluation phase, we consider dynamic programming algorithms which can draw upon knowledge of the precise Markov decision process. But we are not wanting to make that assumption anymore, so instead we'll come up with approximate methods that sample and then do this evaluation phase approximately, and turns out this will still be okay. This can still lead to convergent algorithms. So to recap, for the policy evaluation, in the previous lecture we talked about ways to do this model-free. So here at the top we see an update which could be taken to be a Monte Carlo value update, where, for instance, we're in some episode, maybe depicted N, and at the end of that episode, there was a time step T inside that episode in which we saw a state ST, and from that state onward we saw a return GT, and then we just incrementally update the value of that state towards that. This is showing the update of one state. Of course, we normally, when using Monte Carlo algorithms, we would have to wait until the end of the episode to update all states. So instead of just updating one, we would actually maybe update all of the states in one go. But now I'm going to draw your attention to this target GT, and I'm going to make it explicit that Monte Carlo is one choice. This was all discussed in the previous lecture, where Monte Carlo would use a full return, so the reward plus the discounted next reward plus the doubly discounted reward after that, and so on, which we can write down recursively as well, where the return is the first reward plus the discounted rest of the return. That would be our Monte Carlo target, and we discussed that this is a fine target to use, although it might be quite high variance in some cases. We also talked about alternatives, which might have lower variance, like TD0. TD0, I'm reminding you, is exactly the same algorithm which we could also call one-step TD. And this refers to the fact that we're taking one step in the world, we see one reward, and then we use bootstrapping, which refers to the usage of the value function estimate itself to take the place of the random return. So if we compare it to Monte Carlo, we saw in Monte Carlo we were using the random rest of the return, whereas in Temporal Difference Learning we replaced that with our current estimate of the expected return. This tends to be much lower variance. It can suffer from bias in some cases. So we also discussed intermediate approaches that one can use. For instance, n-step approaches, where we just take a fixed number of steps, in this case n different steps, which means we look at n different rewards, and then we bootstrap the state n steps in the future, which can be written down semi-recursively as well, where the n-step return takes one step and then looks at the n-1 step return. And additionally, we also looked at, well, if you're doing that kind of n steps kind of means you're either continuing or you're not continuing, and then we said we could also do that partially. So we could also on every step decide to bootstrap a little bit with weight 1 minus lambda, and then continue to the rest recursively with lambda. Because this is defined recursively, this means that on the next step, if you would roll this further out, you would again bootstrap a little bit and continue, and then bootstrap a little bit and continue, and so on. For lambda 0, this is exactly the one-step TD algorithm. For lambda 1, this is exactly the Monte Carlo algorithm, and that's also why the one-step approach is sometimes called TD0. So this is just to recap that there's different mechanisms you could use to do model-free policy evaluation. And in each of these cases, the goal was, as in the previous lecture, to estimate the value of the current policy. So there's some policy pi that is used to generate these transitions, to generate the behavior, and we're just estimating the value of that policy. Now, we can consider then improving the policy. We didn't consider that yet last lecture, but in this lecture we want to improve the policy. And one way to do that, as I mentioned, is to make it greedy. However, greedy policy improvement over state value functions does require a model of the Markov decision process. Because the greedy policy would then be something like this, where we take the argmax over this expectation of the transition. That's a bit cumbersome because we are not model free anymore. So now the policy improvement step seems to require a model. But fortunately, there's a way around that. We can just, instead of estimating state values, we could also choose to estimate state action values. And then we can much more easily find the greedy policy by picking just the highest valued action in every state. This would give us a new policy. So Q here could be an estimate of Q pi, of the true value of the policy. And then pi prime could be a greedy policy with respect to these estimates. Then, of course, having a new policy, we could try to estimate that one instead. So this is why we're considering action values, essentially, because it makes it so convenient to then inspect the values of different actions and then infer a policy from this. So now basically the whole idea is to plug in these model-free estimates into the policy evaluation phase of policy iteration. So essentially what we're doing here is we're depicting the same picture as before, but we replace the V's with Q's. So that's a small change, right? We're just considering state action values rather than state values. But for now, we're going to do the exact same thing as before. We're going to estimate the value of the policy and then go greedy. The greedy step is facilitated by using these action values. It's very easy to then, if you have these action values, construct a greedy policy. And this can be done model-free. Now, in order to make the full algorithm model-free, we also want this evaluation step to be model-free. And one way to do that is to use Monte Carlo policy evaluation. So we could just consider following a certain policy and maybe do that indefinitely long, many samples, and we all the way converge to these true action values. In a moment, I will relax this assumption greatly, and we'll see we can even learn from single samples and still do some version of generalized policy iteration. But for now, conceptually, just keep in mind, oh, we're just going to do maybe exhaustive like evaluation of that policy, and then we just consider the greedy policy. So every once so often, after a lot of learning, we change our policy to become greedy. However, there is a problem if we go fully model-free, which is that if we really pick the greedy policy, then we wouldn't explore, which means we wouldn't actually sample all state action pairs when learning by interacting. So why is this a problem? Well, it's a problem because it makes the policy evaluation susceptible to problems. Essentially, if you have a fully greedy policy and you're trying to evaluate that with a Monte Carlo algorithm, that means that you should be following that greedy policy. But if you're following the greedy policy, it might simply not select certain actions in certain states. And that means that we don't have a reliable estimate of the state action value from those actions, which means that then if we consider the evaluation phase, this will be maybe severely hampered. And that means that then the improvement step could be wrong. Because we don't have accurate state action pairs, state action values for certain state action pairs, this means that the improvement step could wrongfully pick a different action. So that is a problem, but it's also not that hard to fix, fortunately. So instead of doing full greedification, we could also consider an epsilon greedy policy, where we still allow with some probability epsilon to pick any action. Turns out this is okay. This is why this procedure is called generalized policy iteration. Recall that for the policy improvement step, we just needed that the policy, new policy, was better, but we don't need this to be fully greedy. So it turns out epsilon greedy can be plugged in here as well. And we depict it now in the figure that we're also not doing a full evaluation phase. So this new line at the bottom is no longer greedy, but it's epsilon greedy. And in addition, we're only going to move partly in the way of the evaluation. So we're no longer going to assume we're going to fully evaluate every policy that we have. Instead, we're just going to do some evaluation, let's say a couple of episodes, and then we consider the epsilon greedy policy with respect to these new action values. So now we have a full model-free algorithm that can be used for policy iteration. And now you might question, well, sure, but you're not doing a full evaluation anymore. You're not doing full greedification. Is this algorithm still sound? Does this still converge to the actual optimal value function and the optimal policy? So first, we're going to just make it very clear what we're doing in terms of the algorithm. So we're going to sample episodes according to our current policy. Then we're going to just do policy evaluation. So we're going to model-free learn the value of that policy. And for instance, we could pick a step size that decays over time, because otherwise we might have irreducible variance, right? Which might make our action values to be quite inaccurate. Although you could also use this algorithm with a fixed step size, and in some cases it might still be fine. But maybe it's better to consider a decaying step size. For instance, that decays with 1 over the number of episodes that you've seen so far. And then in addition to that, it might also be useful to decay the the uniformness of the policy in the epsilon greedy policy. So this would make sure that eventually you're selecting the greedy policy. So this is basically a small change to the epsilon greedy policy where we're just allowing the epsilon to be dependent on the number of episodes you've seen so far, or on the time steps if you prefer. So we see that the evaluation and the exploration are both time dependent here, but on every time step we're doing this approximate version where we have some policy right now, we're evaluating that with some step size and some samples, and then we're going to go partly greedy. And then the reason to pick this epsilon is that it actually has a certain property which is desirable for these theoretical properties. And we call that property greedy in the limit with infinite exploration. So what does that mean? Well, greedy in the limit means that eventually you will become fully greedy. And this is important to actually converge to the optimal policy. Eventually you should just always pick the right action. And you shouldn't have this epsilon probability of picking a wrong action indefinitely. So what we want essentially is eventually you should become fully greedy, but you should also explore infinitely often. So what does the second thing mean? Well, essentially we can formalize that by saying the count for all state action pairs should go infinity as time goes to infinity. This ensures that we are going to evaluate everything properly. So if you continue to select every state action pair indefinitely often, that means you'll eventually have enough data to have a good evaluation of the value of the current policy. And then this means that the greedification step can be trusted. The greedy in the limits can be formalized quite simply as this, where we just say the policy, our stochastic policy, for instance epsilon greedy, as time goes to infinity should eventually become fully greedy with respect to whatever the current action values are then. So note that these two conditions, they kind of pull in opposite directions. Greedy in the limit can, for instance, be achieved by being immediately greedy from the beginning, but then you wouldn't explore infinitely often. Likewise, you could explore infinitely often if you just kept a fixed epsilon, but then you wouldn't be greedy in the limit. So are there exploration policies that do both of these at the same time? And the answer to that is yes. For instance, if you have an epsilon greedy policy that decays the epsilon with 1 over the number of episodes or 1 over the number of time steps in total, this would actually have both these properties if you're careful about decaying the epsilon properly. So you shouldn't decay it too fast, because then you won't be exploring infinitely often, but you should also decay eventually. And this can actually be seen by just summing over all episodes. 1 over k would be proportional, the summation of that over time would be proportional to the logarithm of k, which is a growing function. So if k goes to infinity, this will also go to infinity, albeit very, very slowly. You could also decay your epsilon a little bit slower than this, and that would also be fine. So there's a theorem, and I'm not going to prove that here, I'm just going to state that, basically to reassure you that this is fine. So if you have a greedy in the limit exploration policy, which also explores infinitely often, so a GLE policy, then model-free control with Monte Carlo estimates converges to the optimal action value function in the limit. We'll see a variation of this shortly, which has also been proven, in which you can do this even with shorter evaluation phases. So that's reassuring. We've kept the optimality that we had from our dynamic programming algorithms, but we can do this now in a fully model-free approach. Of course, that was for the Monte Carlo case, and we've talked a lot in previous lecture about benefits of doing temporal difference learning rather than Monte Carlo. So now, maybe somewhat obviously, we're going to turn to that same question, and we're going to see if we can use temporal difference learning for control. So to recap, temporal difference learning has several advantages over Monte Carlo learning. It has lower variance in the updates, it can be used online, and it can also learn from incomplete sequences, which also means that, for instance, if the episodes are really long, or if you only have exactly one episode in your whole lifetime, temporal difference learning can still learn, whereas Monte Carlo would not be able to learn during the episode. So a natural idea would be to use temporal difference methods instead of Monte Carlo methods to do control. So basically we want to apply temporal difference learning to the action value functions to have this same convenience of being able to easily pick a greedy or an epsilon greedy policy. And then, for instance, we could use epsilon greedy policy improvement as before. But we could also continue to update every time step, because temporal difference learning can learn from individual transitions. It doesn't need complete episodes. So one way to do that is the Sarsa algorithm. I briefly talked about this in the previous lecture. Sarsa is just temporal difference learning for state action values, and one way to depict this is to look at this diagram where we start at an action which corresponds to some action A taken from some state S, which is not in the diagram. And then we see some reward R and we reach a new state S prime. And then we consider already what the next action will be under our policy, A prime. And then we use this to construct an update. So our target here will be the immediate reward, as always, plus a discounted next state action value of st plus 1, at plus 1. And we're just going to compare this target to our current estimate as usual, have a small step size to get rid of the variance or the noise in this update, and then we just update our action value functions incrementally using this update. Sarsa comes from the name. Sarsa comes from the usage of a state, action, reward, state, and next action. So that's state, action, reward, state, next action, Sarsa. Now, this is a very natural extension of the temporal difference learning algorithms, and we briefly touched upon it last lecture, but then maybe somewhat obviously you can use this in place of Monte Carlo learning. So this is the proposal. We're just going to do generalized policy iteration again, but now we're actually going to consider, instead of taking full episodes or maybe even multiple episodes, we're actually just going to do this time step by time step. So each evaluation phase will be exactly one time step long, and then we immediately consider the epsilon greedy policy with respect to our new action values. Now, if you think about this, when you do this epsilon greedy policy, the greedy action might not have changed on a single update. So it might be that your policy actually remains fixed for a couple of time steps, which means that the policy evaluation will also last for a couple of time steps. But occasionally, or sometimes maybe fairly often, it might be that the identity of the greedy action does change. And that means that the policy evaluation step can last as short as a single step before you immediately apply this greedification step, this epsilon greedification step. But then the next time step, you'll evaluate this new policy, and we are still doing a version of generalized policy iteration. It might not be immediately obvious that this algorithm is sound and will converge, but actually this has been proven. This is not trivial to prove, and I can give you pointers to papers in which this is proven, but for now I will just assure you that this is a sound algorithm. So this is how that then looks if you want to write it down a little bit more explicitly in pseudocode. This is from Sutton and Bartow, and this is for the tabular algorithm. So we're going to use a capital Q to refer to a specific cell in the table corresponding to some state and action. And then for each state action pair, we're just going to arbitrarily initialize this, for instance at 0. And then we have this double loop where the outer loop is on episodes and the inner loop is on steps within the episode. So each episode starts by initializing the state. Here, think of state as the initial state of your episode, which is given to you by the environment. For instance, the state could simply be the observation, and in the simplest case, the observation could be the full environment state. If you're in a fully observable problem, that would be the case, and then as agent state, you could just use that observation. More generally, when we say state, this should be the agent state. So the initial agent state could also be due from the first observation in the episode, somehow inferred from that. Then we immediately pick an action according to our policy. And the policy is derived somehow from the action value typically. Although it doesn't have to be for this algorithm, we could also be using Sarsa for pure prediction, as we talked about in the previous lecture. But in this case, if we're wanting to do a control, for instance, the policy could derive from our action values and could be epsilon greedy. And then in the episode, we just repeat the following steps, where we actually execute that action in the environment, which means we can then observe a reward and a next state, or a next observation that helps us construct a next state. And then we immediately pick the action that we're going to execute in that next state. And then, again, this is from a policy, for instance, derived from the action values. And then we use that action to update, because we're going to update the state action value by adding this temporal difference error, which is the reward plus the discounted state action value at the next time step, minus our current estimate. And then we will just replace S with S prime and A with A prime, and we start the loop again. So on the next step, we'll actually execute this A prime that we've just chosen. So we picked the action here, and then on the next loop, we'll actually execute it in the world. And then this just continues until the state is terminal, so we've reached the final step of the episode, and then we repeat the next episode. We start again in a new state. So this would be the Sarsa algorithm. It's not too complicated to implement, although you should be careful to get the details correct, because otherwise there will be no learning. And this algorithm, as I promised, there is a theorem that this also converges, and specifically we need the same condition that we needed for Monte Carlo control, which is that the policy should be greedy in the limit with infinite exploration. The greedy in the limit part is to ensure that the action at the next time step will eventually become the greedy action, so that we're actually evaluating the greedy policy instead of evaluating whatever policy we currently happen to follow. That will be a different thing. And the infinite exploration is just to make sure that we actually update all state action values indefinitely often, because otherwise we might have irreducible uncertainty about some of these state action values, which might lead us to draw the wrong conclusions about which policies are preferred. Okay, so that's one way to go, Monte Carlo learning and Sarsa learning. And in both cases, what we're doing is we're interleaving this policy evaluation and this policy improvement step. Now we're going to turn to a new topic, which is OffPolicy Learning, which is about learning about a policy different from the one that we're following. And there's a specific, very popular algorithm that is an off-policy algorithm called Q-learning, which we'll also talk about here. Before we go into explain what off-policy TD and Q-learning are, I'm first going to recap briefly from the dynamic programming lecture that there's different ways to find the value of the optimal policy. And specifically, we talked about these 4 different algorithms essentially that are on the slide, where there's 2 algorithms here for policy evaluation. And we've just discussed how we could use policy evaluation in policy iteration if we interleave the policy evaluation with a policy improvement step. There are also algorithms in dynamic programming which we can use to immediately estimate the value of the optimal policy in a more direct way. And one way to think about this is that we're basically interleaving the greedification very tightly with the evaluation. So this is what value iteration does. And if we look at this equation here, the second equation, what we see is we basically immediately consider the greedy action with respect to one step look ahead according to our model. This is dynamic programming. We'll turn to the model-free approaches in a second. So here we're just assuming that we have a model. So we're just going to consider the maximum value if we roll the model forward one step and then bootstrap on our current estimates that we have. So basically you can view this as immediately doing a greedification of this estimate in one tight loop. And value iteration, as we have discussed, or Diana has discussed, will also converge, and it will converge to the optimal value function, and hence you can infer the optimal policy. And then for both these categories, policy evaluation and value iteration, there are 2 variants, one for state value learning and one for state action value learning. So we see these V state values and Q state action values. We notice that the policy evaluation for state action values looks a lot like Sarsa, and indeed there's a strong relationship to those. And indeed, all of these algorithms can be, well, not all of them, but many of them can be turned into model-free algorithms, which is what we're going to do here. So we already talked about temporal difference learning in the previous lecture and Sarsa in the previous lecture and also just now, which can be viewed as sampling the policy evaluation algorithms, going back to the previous slide, where there's an expectation here, which we can sample according to our current policy, and then we can use this as a target to update slightly towards. In doing so, we introduce a step size to only make a small step because we will have a noisy target, unlike in dynamic programming, and hence we want to somehow average out the noise, and for this we use a small step size to make sure that we don't jump too far and that the updates become too noisy. And then we can see that TD corresponds to sampling this first one, whereas Sarsa corresponds to sampling this third one. But there's a third algorithm, and that algorithm is called Q-learning, and it corresponds to sampling this last equation, where there's also an expectation outside, but there's a value iteration equation here, which has a maximization over the actions inside. I talked a little bit about value iteration here on the second line, where we immediately go for greedy. In this last line, because we're considering a state and action, we're actually already conditioning on that first action. So that one can't be taken to be greedy. That's just for any action you can do this evaluation. But then we can still roll forward one step and consider in the next state the greedy action, the one that maximizes your action values. This is still a valid value iteration algorithm, and it's one that we can sample, which we've done here. So we see that Q-learning takes our state action value and updates it very analogously to Sarsa, where the only difference is how we bootstrap. Instead of considering the next action in the next state, we consider the best action that we could possibly take according to our current estimates, and then use that as our estimate for the greedy value of our current value function, and back that up. Note that there's no trivial analogous sampled version of this algorithm, which is the value iteration algorithm for state values. And I want to encourage you to briefly think about that. Why would that be the case? Why are there 4 dynamic programming algorithms and only 3 model-free algorithms on these slides? So feel free to pause the video whenever you want to take a second to think about these things. I will now immediately give the answer to that, which is that it's in some sense a convenience thing, where out of these dynamic programming equations, 3 of them have the expectation on the outside, so it's very convenient to sample that. but the value iteration for state value functions has the maximization outside the expectation, and that means that it's non-trivial to sample this. It's not immediately obvious what the model-free algorithm should look like if you wanted to do this. So that's why we don't have an analogous model-free algorithm here. Okay, now I want to make the distinction between on-policy and off-policy learning in some generality, and I will connect this to this new Q-learning algorithm. On-policy learning is about learning from a behavior, about a behavior policy from experience sampled from that policy. That's what we've been discussing so far. For the Monte Carlo control algorithm and for Sarsa, and also in the previous lecture on policy evaluation, we always considered there was just one policy, and that policy would be used to generate your behavior because you want to make predictions about the value of that policy. We call that on-policy learning because we're learning about the policy that we're following. We could also consider off-policy learning, which refers to everything else. So on-policy learning is in some sense a specific case, and off-policy learning is everything else, which means that we're learning about a target policy pi, but the experience sample is from a different policy, which we could call mu. Sometimes in the literature, the terminology is slightly different. Sometimes people use B instead of mu. That's kind of not too relevant. We'll try to consistently use mu for the behavior in the upcoming slides, and then pi for the target policy. So please keep that in mind, that mu is also just a policy to select actions. It's a distribution over actions in each state. It could be deterministic if you wish. And then we want to learn about a potentially different policy, a target policy pi. This refers essentially to learning counterfactual about what-ifs, about things you could be doing. So to give you some examples, for instance, you could have a question. This is a valid predictive question. What if I would turn left? Maybe you're not turning left all of the time, or maybe you're turning left occasionally in some cases, but not in others, like consistently. It could also be that you have a random policy that turns left stochastically every once so often, rather than occasionally. And then we could have a question that is, but what if I would turn left all the time? So that could lead to new observations, new rewards. Or we could have a question when we're playing a game, what if I would have played more defensively? Would this change my win probability? Or we could, for instance, ask, what if I would continue to go forward? Let's say you're a robot and you make predictions about how many steps until I bump into a wall. That could be a value function where the reward could just be the number of steps, and the episode termination could be when you bump into the wall. That's a valid predictive question. But if we don't follow that behavior all the time, then we might still want to make this prediction. So I haven't told you here how to make those predictions, how to use your data to learn these things, but I just want you to realize and think about these as valid predictive questions that could be helpful for an agent in the world, and maybe you even want to ask multiple of these questions. These are off-policy questions because they refer to asking questions about what-if behavior that I'm not currently maybe doing all the time. So in general, we want to evaluate a target policy to compute the estimated value of that policy, either the state value or state action value. And we're using a different policy, mu, to actually generate the actions. So why is this important? Well, one reason why you might want to do this is you might want to learn from a database. Let's say you have some stored experience, for instance, observed from human behavior or from other agents, from, for instance, data that was logged somewhere. The behavior there is not under your control, so there is just some frequency of actions being selected in the data. And maybe you have a what-if question. What if we would have instead followed this strategy? Of course, that strategy should be supported by the data. There should be some samples in the data that will support and give you data about that question. Otherwise, you can't learn. But this is a valid question that you could have where the experience might differ slightly. For instance, all actions might be selected under the database, but not in the same frequencies as you want to consider them. And then learning off policy is kind of a natural thing to be doing. Somewhat similarly, you might want to reuse your own old experience. So far, we've considered algorithms that learn online. So they basically consume data and they update themselves. Or they wait until the end of the episode, like Monte Carlo does, and they update everything at the end of the episode. But then the data is thrown away and you move into the new episode and you only use the information from the new episode to update your policy from that point onwards. Now, arguably, this is potentially a little bit wasteful, and indeed it's a fairly popular approach to store the data that you've seen and try to reuse that to learn more. But that means, if we're doing control, that your policy may have changed in the meantime. when you were collecting the data, you may have had a worse policy, for instance, or just a different policy, or you could have been exploring more at the beginning. So that means that in general, the behavior policy, the probabilities of selecting certain actions might be quite different in your old data than it is currently. But you might still want to learn about it. You might still want to use it. Separately, in addition to these other cases, you could also want to learn about multiple things at the same time. So this is related to these what-if questions that I showed on the previous slide, where even if we're following one policy and we're not trying to learn from past data or from other sources of data, we might still want to learn about many things, many what-if questions, because this is a way to accumulate knowledge about the world. So that refers to learning about multiple policies, and then therefore all but one of these policies should be OffPolicy. At most, one can be exactly your behavior policy. So any other policies would be, you would require OffPolicy learning to learn about them. And finally, now we're going to turn towards this one a little bit more in detail. You might want to learn about the greedy policy while following an exploratory policy. This one is maybe obvious in the context of policy iteration, where we're always interested in this policy improvement step, which can be implemented by making your value functions or your policy greedy with respect to your value functions. So it's a valid question to ask, what is the value of the greedy policy? Because that's the policy that we're going to consider next. But we might not just want to sample from that greedy policy because of reasons I mentioned before that you might not explore sufficiently often. This brings us back to this Q-learning algorithm. Q-learning estimates the value of the greedy policy. It's conditioned on the state action pair. Oh, sorry, this S and A should be ST and AT. So we're considering a specific state and action pair, and then we're taking one step, the reward, and then in the next state we consider acting greedily. So we are learning about the value if you take this action, but then in the next step you would be greedy. And that's a valid target to update, and it would be learning about the greedy policy, but you don't want to necessarily act all the time according to that policy, because that wouldn't explore sufficiently. Now, fortunately, it turns out if you do this Q-learning algorithm, if you do the tabular version specifically, then you will converge to the optimal action value function as long as we take each action in each state infinitely often. Now this might sound similar to what I said about Sarsa, but there's an important difference here, which is that you don't actually need your behavior to become greedy. In fact, Q-learning can learn the optimal value function eventually, even when you explore uniformly at random throughout your lifetime. Of course, to have actual convergence, because this is a random process and you'll have random data, this is only true in the limit. So you do need to get infinite data in the limit, but you don't actually have to make your policy greedy anymore. That's a big difference between Q-learning and Sarsa. So this works for any policy that eventually selects all actions sufficiently often. The uniform policy is one example. Epsilon greedy would be a different example, but we no longer have to decay the epsilon. You do require appropriately decaying step sizes. This is true for all of these algorithms, including Sarsa, but also for policy evaluation with temporal difference learning. And for instance, the Robbins-Monroe conditions, as they are called, suffice to have that. And these conditions are that your step size is chosen to be such that if you sum over all time steps until infinity, that in total your step size will be infinitely large. This ensures that from any state action value estimates that you currently have, you can always move far enough to find new estimates that are more optimal. And then in addition to that, we want that the sum over all time steps of the squared step size is less than infinite. It's a finite number. This essentially ensures that eventually your step size becomes small enough that eventually you cancel out all the noise, that you eventually start averaging enough data in that you can get rid of all of your uncertainties. These two conditions together ensure convergence of the Q-learning algorithm if you also explore indefinitely. And for instance, a specific choice that you can consider here is 1 divided by the time step to the power omega, where omega is somewhere between 1/2 and 1. So the extremes here are 1 over t or 1 over square root of t on the other hand. If you would pick anywhere between those, you would have these conditions. So that would be a suitable step size parameter. And we can see that basically the step size would then decay over time, and eventually you make smaller and smaller updates. So that kind of tells us that Q-learning is a good algorithm that we can use. And now I'm going to step through an example a little bit in more detail to show you the differences between Q-Learning and Sarsa. So for the example, we'll go to the blackboard, essentially. And let me just depict some state, which you could call S. And maybe there's some action you could take, and there's some other action you could take. And let's say, for instance, that we've taken this action below here. Let's call that A. And then from this, we transition to a next state. Maybe for argument's sake, let's say we transition deterministically. There could be multiple states, of course, that we end up. And then we consider another step. And there's also some reward along the way here. Let's say that the reward was +1 or something of the form. And let's consider this one transition here, where we were in a state, we took an action, we saw a reward, and we saw a next state. Now let's arbitrarily say that here initially our action value function was, let's say for this arrow pointing downwards, was say 1. Then we could consider what happens if we use Sarsa or Q-Learning to update this action value function. Now, in order to fully update, we have to establish a little bit more. So let's say that discount factor is 1/2 for concreteness of the argument. And let's say that we have some estimates. So here, let's say that our Q estimate of S prime for the up action might be, for instance, let's say +4. And then we also need some sort of an estimate for the down action. I haven't yet told you which action we're going to take. We'll get to that in a moment. And let's say the down action is only worth 2, according to our current estimates. Now these are not the true values, these are just our current estimates. Then we could consider what the targets are that Q-Learning, Q-Learning or Sarsa would use. Now let's say that we've actually selected this action to go down. Then Q-Learning doesn't actually care too much about which action you've actually taken. So the target there would be reward plus discounted maximum action in the next state, which in this case would be +1 for the reward, plus 1/2, which is our discount factor. And then we look at this max action in the next state, which in this case would be +4. So in total, this would give us a target of 3. So depending on our step size, we had an estimate of 1 to start with. And then depending on our estimate, or depending on our step size, we would update this estimate some portion upwards, but it would be updated in any case upwards towards 3. Phrased differently, our temporal difference error would be +2, and then we add whatever our step size is times that temporal difference error to our estimate. So for instance, to make that very concrete, if our step size would be 0.1, our new estimate would be 1.2. You can calculate that yourself if you wish. Now Sarsa needs the actual action that we selected. So let's say, for argument's sake, so first let's write down the Sarsa update. It takes the next state and the next action into account. Let's say, for argument's sake, that it selected the action to go down. Then everything else is the same. The reward is the same, the discount is the same, but the next value would be +2. It's the value of the action of taking down, which would mean that Sarsa would only give you a +2. Or, alternatively, if the up action was taken, it could also have generated a target of +3. So if A prime is down, this is what happens. And if A prime is up, This is all the same, but the update is slightly different. So we can see that Sarsa would perform the exact same update if it would happen to pick the greedy action, but there's some probability that it would select a different action and then the update would be different. That's okay, it doesn't mean that one is necessarily better than the other, and in fact in both cases here the target would be higher than our current estimate, so we would update our estimate value a little bit upwards. But of course if we see a +2 as a target, we would update it upwards less than if we would see a +3. One could also say that if in fact our policy was uniformly at random, let's say it would pick both of these actions with the same probability, then in expectation the Sarsa target would be 2.5 instead of 2 or 3. Okay, so I want to conclude the example for now there, and we'll go back to the slides. So now I actually want to show you another example that would illustrate differences between Sarsa and Q-learning. And now we're going to use both these algorithms for control, so we're trying to optimize something. And this is called the cliff world, or it's just a cliff walking example as it says on the slide. And I'm going to explain the example to you, and then I'm going to explain the plot that you can see below. So the example is quite simple. It's kind of a grid world where you start in state S, and on every step you get a reward of -1. There's no discounting, so your total reward in an episode will simply be the number of steps you've taken. And then there's a goal all the way on the right hand side. And if you reach that goal, you end your episode. This is beneficial because it means that the -1s stop, so you're actually encouraged to find the goal as quickly as possible, because the maximum value would be attained if you're minimizing the number of steps you take in an episode. Now there's an additional important thing happening here, which is that there's this region here at the bottom called the cliff, and if you step into that, you get a reward of -100 and you transition back to the starting state. I believe this also terminates your episode, so the episode would then end with a -100. So what would be the optimal thing to do here? Well, the optimal policy is shown in the figure, and it would actually start here in the start state, as always, would go up 1 and then it would walk right past the cliff. And then it would go down onto the goal. You could also consider a safe path. You could go a couple of steps away from the cliff and then walk according to the safer path. Now, we want to learn the optimal value function in this problem, perhaps, and we want to have the optimal behavior. But we know we can't not explore because we are assuming here that the agent doesn't know the structure of the problem, otherwise we could use dynamic programming. So instead we're just going to learn from experience, and we're not going to assume that the agent knows everything. So it has to try each action in each state. And we'll try these two different algorithms, Sarsa or Q-learning, to learn in this example. And we're going to use an epsilon greedy policy here. Now what you see here at the bottom, quite interestingly, is the actual rewards per episode, that these different algorithms attain throughout learning. And we can see that after less than 100 episodes, maybe after even 50 episodes or so, the algorithms have both stabilized apparently to a certain policy, which gives them a certain amount of reward per episode. Interestingly, Sarsa has stabilized around -25, which means that it takes roughly 25 steps to reach the goal, whereas Q-learning has stabilized around -50. Does that mean that Q-learning also takes roughly around 50 steps? No, actually. It means that Q-learning regularly falls into the cliff. So why does this happen? Why does Q-learning perform worse here than Sarsa? Didn't I explain that both of them are optimal in the sense that they converge to the optimal policy? And in fact, I didn't say that we're decaying the epsilon here, which we're not. And didn't we say that Q-learning can converge to the optimal value function when we don't decay the epsilon, whereas Sarsa cannot? So what gives here? Why is Sarsa performing better than Q-learning? The reason is that Sarsa is an OnPolicy algorithm. And being an OnPolicy algorithm, this means that Sarsa will evaluate the policy that we're actually following and will give us valid estimates, accurate estimates for that policy. So at first the policy is changing, right? But at some points it will kind of stabilize, even though we still have an epsilon. So there will be some randomness to the policy, but the policy will be stable because the epsilon is not changing, but also because the action values won't change that much anymore. And that means that even though the epsilon greedy policy depends on your action values, if your action values don't change that much anymore, the policy can become quite stable. But this policy does explore, and that means that there's some non-zero probability that the policy will actually fall into the cliff, and that's captured here in these average rewards per episode. So what does Sarsa do? Sarsa, being an OnPolicy algorithm, accurately estimates that if you have this epsilon, if there's a probability to explore, then if you would be very close to the cliff, there's a pretty high probability that you'll fall in it. Let's say the epsilon is 0.1, that means that 10% of the time you pick a random action from this state. So this could mean that you either go back, or you go up, or you go right, or you fall into the cliff. So if you try to walk along this optimal path, there are many opportunities for the algorithm to step into the cliff and get this reward of minus 100. Sarsa is estimating these values. So basically Sarsa is saying, well, if I have a choice, maybe I shouldn't walk so close to the cliff because I know I will explore. I know that there will be some randomness in my policy. I know what the value is of that policy. And turns out maybe then if I'm very close to the cliff, the higher valued action is to actually step away from the cliff first, to this safer path, which is a couple of steps away from the cliff, in which you can reliably get to the goal. Because if on the safe path you pick a random action, you could step down, but then you have an opportunity to step up again on the next step. Of course, occasionally it can happen that you explore twice in a row, and it could be that you step down randomly and then step down again. But then if you're on the safe path, at least you can recover again immediately. Whereas if you're immediately next to the cliff, just one exploratory action will toss you in. So why then is Q-learning performing worse? Well, what we're evaluating here is the actual rewards per episodes, which does include this exploration. This means that Q-learning has estimated, maybe by now accurately, the values of the optimal policy. And maybe the values of the optimal policies will tell you, or actually quite likely the values of the optimal policy will tell you to walk along this optimal path. But then if you execute an epsilon greedy algorithm around this, the epsilon greedy algorithm will try to walk along the path, but occasionally will be bumped back or up, but then occasionally will also fall into the cliff. So on average, because Q-learning is not taking into account that it's actually exploring, it will do worse. If, however, you would take both these algorithms, let's say here at the end of learning, and then you would look at the action values and then execute the greedy policy according to both these algorithms, then Q-learning would actually have found a shorter path, and it would actually walk very reliably next to the cliff without any exploration towards the goal. So it really depends what you're after here. Sarsa does better because it takes into account the exploration that we're doing, but Q-learning has actually found a more optimal policy if we would only execute that policy instead of the exploratory one. This is more meant to illustrate differences between on and off policy learning than it is to say Sarsa is better than Q-learning or vice versa. But it's important to appreciate these algorithms have different properties, and this is meant to illustrate one of these properties. Okay, now we're going to turn towards a different topic, which is a different failure mode for Q-learning, because it is known that Q-learning can overestimate the action values. So this is about classical Q-learning as discussed before. And the issue that we're going to talk about is related to the following. So first we're just going to write out this bootstrap target that is used in Q-learning. As mentioned before, we're just looking at the action values, we're picking the highest one. We can actually write this down differently, as done on the slide, where we consider the argmax, which means the maximum element of our estimate at st plus 1. And we could consider that basically to be a policy, right? We're picking a policy, and specifically we're picking the policy that is greedy with respect to these action values. And we can write it down a little bit verbosely, a little bit like more explicitly over here, by saying there's a policy that picks the highest valued action, maybe breaking ties equally or something like that, and then we consider evaluating the value of that action. This is equivalent to just taking the maximum action value. But writing it out like this, we can notice that we're actually using the same value function to select this action and then to evaluate the action. But these action values are approximate. This in particular means they could be wrong. And what this means in practice is that you're actually more likely to select an action value that happens to be high then you are to select one that happens to be low. So what this means is if these values have some noise, they're wrong because you only have finite samples, or because you're doing function approximation, or all sorts of reasons why your action values might be wrong, then in fact some will be estimated slightly too high by accident, others will be estimated slightly too low by accident. But this phase here where we're selecting the action will very likely pick an action that is overestimated, much more likely than to pick one that is underestimated, especially if the true values are fairly close together. Let's say our true action values in this state are actually all 0. But so far we've seen limited data and we don't have accurate estimates for all of them yet. You don't know yet that they're actually all 0. So you think some of them are positive, some of them are negative. But then picking exactly according to the same function to evaluate it, we are picking an action that has a high value, and then we're saying, oh yeah, I picked that because it has a high value, and now the value is high. That means we have an upward bias. So let's illustrate this with an example. So consider the game of roulette. This is a gambling game played in casinos, and I'll briefly explain the game. Details are not too important, but we're going to formalize the game as follows, where we have one state, which is that we're at the table and we're playing. And in this state, we're going to consider 171 different actions. This is because there's actually 170 different options of plays you can do on the roulette table. Roulette is a game in which a number is drawn at random by placing a little ball on a spinning table, and then the ball will fall into a slot, and the slot will correspond to some number. The number will also have a color, so the number could be a red number or a black number. And I believe the numbers go from 1 to 36 or something of the form. In addition to just being able to pick a number or a color, you could also pick whether the number is odd or even, or whether it's in the first half of the number, so 1 to 18, or in the second half, 19 to 36. So there's all sorts of different bets you can place. And then in addition to all of these, there's a number 0, which doesn't actually have a color. So it's not covered in any of those, and it's not considered odd or even. So the number 0 is green, and you can bet on 0, but it won't actually pay out if you have chosen either red or black as a bet. Then these bets, they will pay out, and what they will pay out is associated to the likelihood of it happening. So if you bet $1 on red, and a red number comes up, you get $2. If you bet $1 on specifically the number 17, and then 17 comes up, you get $36. So that means that the win probabilities are random, obviously, and on average you'll actually lose on every action a little bit, because this 0 could come up. Now our actions here, as we formalized it, not to make it too complicated, is we're always just going to bet exactly $1. This is to avoid any issues with also having to pick the betting amount, which would blow up the action space potentially enormously. In addition to this, we're not going to take into account your current funds, so we're not going to consider you being able to go bankrupt. So instead, the action will just be you pick a play to make, you bet $1, and you get your reward associated with that, and then you can transition back to exactly the same state again, so then you can play again. And then there's one additional action, which is to stop to play, which will pay out 0. So you either play a betting action and then you can play again and again and again, or on every of these time steps you can always choose to walk away. So all the other actions that don't stop the play will have high variance, and it will have a negative expected value because of the existence of this 0 on the roulette board. Betting actions do not end the episode, so you can continue to play indefinitely. Okay, I hope that's somewhat clear. So the idea here is that this is a fairly high noise environment, which means that our action values will be fairly inaccurate for a while at the beginning. But it's a valid Markov decision process, and we can consider doing Q-learning, and Q-learning is known to converge to the optimal values eventually. So it's an interesting question to see how well it fares here. And then what we find is that it actually performs rather poorly. So what we see here is the expected profit according to the Q-learning algorithm. So we're basically just looking at the values that it's estimating, so the action value estimates. And what we see here is there's some discount factor here at play as well. I think it's probably 0.99, but I should look that up. But we can see here that Q-learning essentially thinks that even after updating all of the actions 100,000 times, so we've seen 70 million samples in total, for a tabular Q-learning algorithm with just one state, we see that Q-learning is nowhere near the actual values. It still thinks it can actually win more than $20 as long as it just keeps on playing. So that's rather bad, because it means that Q-learning is in some sense something of a gambling addict here. And the actual values is much, much lower, and also Q-learning doesn't seem to be getting much closer. So that's, in the picture, a little bit misleading. It seems Q-learning has fully stabilized. It hasn't fully stabilized. This is actually using a decaying step size, and Q-learning is actually guaranteed to converge, but the convergence will be extremely slow. That's what's happening here. So eventually Q-learning will get there, but much slower than is practical. We've avoided any issues with exploration, just for this example, just to make it sure that we're not conflating anything. And therefore we've just selected every action simultaneously on every time step. So instead of just picking one action, we're just picking all of them at once, sampling the reward for each of these actions at once, and then updating the action value function for each of the actions at once. And then we just do that 100,000 times. So that's pretty bad, and this, you could imagine this showing up in larger problems as well. Of course, this is a small contrived problem of specifically a betting problem, but you can consider this to be part of a much larger MDP. Let's say you're literally trying to learn a robot how to act in the world, and maybe the robot has some sort of a money amount, which is maybe somehow part of its reward function. And then there's a casino in this world. So at some point the robot could walk into the casino, could start playing, and could find itself in a little sub-slice of the real big problem, which corresponds to the smaller problem. Then if that robot would be doing Q-learning, it would still stay at the table and think it would win if only it could play longer and longer and longer. So that seems problematic. So there's a question here, can we fix this? Fortunately, there are ways we can go around that, and we can go back to the main source of the problem here. So Q-learning essentially overestimates because it uses the same value function to select an action to evaluate, the greedy action, and then to use the same value function to actually evaluate that action. So the solution here is to decouple those two. So in roulette, to make it concrete, it's quite likely that some of the betting actions that you've done so far will have won on average. Maybe slightly more often an even number has come up than an odd number, or maybe the number 14 has popped up slightly more often than would be expected on average. There's always going to be some actions that will have won more than they will do in the long run. But that means that on every step, Q-learning, transitioning back to that same state, thinks, yeah, now I played an action that didn't quite win, but on the next step I could play an action that does win. There's always an action left that does look good, or at least for a very long time. So Q-learning will then update as if this state that we transition back to actually has a high value, because it literally picks the maximum that it could and therefore maximizes over all of the noise in the estimates. And the solution, as I said, is to decouple the selection from evaluation, which we can do as follows. And this algorithm is called double Q-learning. So the double here refers to the fact that we're going to actually maintain two different state action value functions. And we're going to basically introduce a new action value function Q prime. So in equation 1 here, we see that we have our standard thing with the one-step reward and the discounted value of the next state. But the value of the next state is defined by picking an action according to our normal action value function Q, but then evaluating the value of that action with Q prime. We could also do the inverse. We could pick according to Q prime and then evaluate according to Q. What we can do then is we can use each of these as targets for these two different action value functions. So on every time step, what we'll do is we'll pick one of the action value functions to be updated, so either Q or Q prime. And then if we pick Q, we use equation 1 to update it. And if we pick Q prime, we use equation 2. But we never update both at the same time because this would correlate them, and then we would just be doing Q-learning again. But if instead we pick either one or the other, this decorrelates the action values. They see similar data, but different subslices of the data. And this means that we can get a somewhat unbiased estimate of the greedy action according to one of them. So we're still picking greedy. This greedification step, this selection process, is still likely to pick an action with a high value. But inasmuch as that value is purely high because of, for instance, random noise, then having a separate evaluation learn on different data might help us to get an unbiased estimate for the value of that policy. So that's the whole algorithm essentially, but we don't have to actually throw away data, so we don't have to only consider one of these action values when we actually want to then infer a policy. Let's say we want to act epsilon greedily, or eventually we want to select a greedy policy with respect to this data, then we can use both action values. So the policy itself, the way we select our actions, can be based, for instance, on the average of the two value estimates. So we're not losing any data in the sense that we might need double the amount of data or something like that. No, that's not necessarily true. We can still merge them together to get our estimates as we use it for the policy. We can also actually prove that Q-learning, double Q-learning does converge to the same optimal policy under the same conditions as Q-learning, which is nice. This tells us that we can trust this algorithm, that asymptotically, in the tabular case at least, it does converge under the same properties that Q-learning does. So that means that the algorithm is sound, but is it effective? Does it do what we want it to do? So obviously we can apply this to to the roulette example that we've seen before, and we find that indeed it does much, much better. By decoupling the selection and the evaluation, we see that it's much more accurate in its value estimates, and indeed this also means that the optimal thing to do according to the estimates learned by double Q learning is to walk away from the table. Actually, it turns out this is not specific to this tiny example, and we've seen previously a video of an agent playing Atari games. I mentioned briefly that this algorithm was using something called DQN. DQN is short for Deep Q Network. Essentially, what's happening there is we're using the Q-learning update with deep neural networks. And that's very effective, and it was actually also using epsilon greedy, so you now know most that you need to know to implement a DQN algorithm, but we'll go into more detail in a later lecture. And then we can apply this idea of double Q-learning to this algorithm, because it's using Q-learning, and therefore it might be susceptible to these overestimations. So double DQN does something very similar to the double Q-learning algorithm as I explained it just now, with a slight difference, because something I haven't explained yet is that DQN uses something that is called a target network, which is already a separate network. So DQN already uses a separate network to bootstrap on, but this was used more as a stability thing, where this separate network is just a slow moving copy of your Q function that you're updating as you go. And then because we already have a separate network, this makes implementation of double Q-learning quite simple, because we can just use that separate network to evaluate the actions, but we could still pick the actions according to the online network that we're updating all the time. These details might be a little bit fuzzy for now, because we haven't fully explained DQN yet. That's okay. The main purpose for this slide is to show that if you apply something like double Q-learning at scale to these Atari games, then indeed we also see a large gain in performance. So the red here on the right hand side will be Q-learning, how well it performed across all of these different Atari games, and then the blue is double DQN, which is basically like a one-line change in terms of the full algorithm. So what does this mean? This means that double Q-learning might be important in practice, and indeed it's quite a common component these days of many deep RL algorithms. And the reason why it's important is because these overestimations, they do actually happen. They don't just happen because of random noise, as in the roulette example, they also happen because of function approximation inaccuracies. So there's various reasons why your value estimates might be inaccurate, and then double learning can be quite useful to help mitigate that. It's more general than double Q-learning, and it can be generalized to other updates. For instance, if we're doing Sarsa, you might think you're safe because there's no max in the Sarsa updates. We're just looking at the actual value of the next action. But turns out that's not quite sufficient to be safe, because we're still actually picking that action because it has a high value if we're doing something like greedy or epsilon greedy. So that means that Sarsa can also overestimate, and then therefore we can also think about using the same solution. This could lead to something we could call double Sarsa, where we still use two action value estimates. So now let's go back to the example that we've seen before and look at what double learning would do in that case. So let's go back to the example, and let's maybe pick a different color. Let's say yellow. And what we need for double learning is we need a separate value function estimate. So let's say that these estimates here at the next state, they were just random, and we could have maintained a separate estimate in that state for both these actions. And for instance, maybe this +4 was actually a little bit randomly chosen, and maybe it could also have been 0. And maybe in this other action, for going down, maybe we could have had an estimate. It's maybe also 0, let's say. Just randomly, we pick two values here. So what we're alluding to here is that this estimate of +4 was actually quite random, and it could have been anything else. And similarly, this estimate of +2 that we had could also have been anything else. And maybe we could also have had an estimate of 0 in both these cases. I'm not saying one is necessarily more accurate than the other or anything like that. I'm just saying, okay, this is another estimate that could have been the case, just to go through the update a little bit. So if this is the case, then we can look at the double Q-learning update, and we can just look at what it does. So let's write down double Q-learning here. And let's remind us of the update. Let's consider that we're also still interested in updating the action value for Q. So we've randomly picked between Q and Q prime. We randomly picked Q now. And then we would have the same thing where we have the reward plus the discount. But then in the next state, we would have the arg max of over action values. And in fact, let me use the eraser and let me give this a different color. Let's just pick that one. We're going to use Q prime to estimate. So that's the difference between Q learning and double Q learning, that we're using Q prime there. And this would then be equal to +1 again. That's the same everywhere. Plus the discount is the same everywhere. Okay, so what does this look like? This is going to evaluate the greedy action according to our online Q. So the greedy action would be up because it has a higher value according to that online value that we're updating, but we're going to evaluate this other value, and that means that we're going to actually evaluate it at 0, which means that our update would tell us go to +1. Actually, that means that our estimate won't change. So we can clearly see here that double Q-learning constructs a target which is not just different from Q-learning in this case, but it's actually also lower. That's a little bit by chance, because it could have been, of course, that these evaluations were different. Like this 0 over here could have also been 7 or something else. But by and large, it is true that double Q-learning tends to pick lower values because Q-learning does this selection. So for instance, it could also have been, if both these actions actually have the same value, it could also have been that this one was +2 and this one was +4. So the other way around from Q-learning. In that case, double Q-learning here would update towards +2 rather than towards +4. Let me get rid of those for simplicity. Now we could also consider updating Q prime. I didn't say what Q prime was on the starting state, so we could also pick something random here. Sorry. So we could also say Q prime of this state of going down. Maybe this was, let's say for simplicity, that is also 1. And then let's consider what happens if we're updating Q prime. So this would be if updating Q, and then if updating Q prime, double Q learning would do R plus gamma Q S prime, and then would take the arg max of, and now let me change colors again, Q prime. Reward is the same, discount is the same, but now we're going to pick greedy according to Q prime. Well, they both actually have the same value, so maybe we could also consider the policy to be uniform across these two. We could either break ties randomly if we consider the values to be exactly the same, but we could also just say let's do it 50-50. So let's just average both these values, so this would then be +3, which means we'd get something that is 1 plus 1.5 would be 2.5. So if we happen to choose to update Q, we would actually keep it the same. The target would be the same as our current estimate. But if we happen to update Q prime was estimated at 1 and seems to be a little bit low compared to the estimation according to Q in the next state. Again, I'm stressing here that we're actually not saying that necessarily one of these updates in this example is better than the other. This is just to show you the mechanics of the update. This can be quite useful. And in fact, if you implement these algorithms, it can also be quite useful to actually just go through a couple of steps and print a lot of stuff. So just look at what the actual updates are that you're doing. Like, how are the values changing? Does it make sense how they're changing? You can do this in the long term. You could plot all sorts of statistics, but it can also be helpful to actually really go into the small little details and look at this step by step. Okay, so this is just to show you the mechanics of the updates, and now let's go back to the slides. We're going to move on to more generically off-policy learning. We talked before about different reasons to do off-policy learning, and then we went into some detail to talk about off-policy learning for the greedy policy, because this is useful for value iteration and policy iteration style algorithms. Now we're going to talk more generally about off-policy learning, and specifically we're going to talk about how to use important sampling corrections to do this. So just to recap, to recall, off-policy learning means learning about one policy, pi, and we call that the target policy, from some experience generated according to a different policy, mu. Q-learning is one example where pi is the greedy policy according to your current action value estimates, and mu can be any exploratory policy. But there are other options as well, and fortunately there are some general tools that can help us with this. But there's one important caveat you just basically keep in mind throughout, which is that you can never expect to learn about things that you never do, right? You can't expect to learn about a policy if this policy contains actions that you would literally never take according to your behavior policy. Then you simply don't have the data to support this. So we're first going to say this a little bit more in general. So the goal is to find some function f with random inputs x and a distribution d prime, given some function f with random inputs x and some distribution d prime, we want to actually estimate the expectation of f of x under a different distribution. And the solution to this is to reweight the function. So the idea here is that this function is going to shortly be the update to our weights. So we have some sort of an update to our weights under some sort of distribution, and we want to reweight this as if we're doing the update under a different distribution. So let's very briefly step through these steps. They're not complicated. We have some expectation of this function of x under some data distribution d in this case. And this is what we want, right? We want to actually sample fx under some distribution d. But we don't have d, we don't have that distribution. We're generating the data under a different distribution. So let's first write out what this thing means. It's just the summation over all x, or the integral if it's a continuous space, but we're just going to merge all of that into this one notation, of all x, of the probability of x, and then times the function of x. What we can do is we can rewrite this in a form that looks a lot like an expectation under d prime by just simply multiplying by d prime and also dividing by d prime. And this we can write again as an expectation, and we notice that the thing inside is now d divided by d prime for every x times f of x. What does this mean? This means if we sample this final thing, we would actually get an unbiased estimate of the thing that we were looking for on the left-hand side. These are all just equations, so these are all equalities, sorry. So that means that we can actually do this, we can sample this thing and get actually an unbiased estimate for this thing that we started off with. There is an assumption here, of course, which is that the data should support, as I mentioned before, which we can also see here in the ratio. You never want to actually divide by 0, right? This means that whenever d is non-zero, d prime also needs to be non-zero. Otherwise, this is not well defined and you can't actually do this. And this is related to this caveat, which sounds maybe much more intuitive, but here's the mathematical side of this. And the intuitive explanation was, well, if you never actually do anything, if you've never actually sampled a certain x under d prime, you can't expect to learn from it. So this is the generic strategy that we're going to use. And the intuition is that we're going to scale up events that are rare under D prime but common under D, because then D prime will be small but D will be large. And that's appropriate because we're going to basically have D prime, right? That's our sampling distribution. And if things only very rarely happen, they're only very rarely sampled in your data, but they would be very common under the distribution that you care about, then obviously you should scale them up in some sense, right? And of course, conversely, if they're very common under your data distribution, but they would be very uncommon, or maybe even would never occur, D can be 0, that's okay, then you would scale them down. So basically, we're just going to average all of the events that we see, these random events, and we're going to reweight the averaging so that the distribution that results from the reweighting is appropriate. That's the generic idea. And now we're going to apply this to reinforcement learning, and we're going to start simple. So we're first going to apply this to one-step rewards. Let's say you are doing policy evaluation for a bandit, but you're sampling according to a different policy than the one you're interested in. So our behavior will be mu as before, and we're just going to consider the expected reward and the expected reward only. We'll get to value functions in a moment. So we can again write this out as an explicit expectation by summing over all the possible actions and writing down the reward as an explicit function of the state action pair. I'm using this notation here. RSA is the expected reward given that you both have the state and the action. This is just shorthand. If you have both the state and the action, the expected reward itself doesn't depend on your policy anymore. Then we're going to do the same trick again. We're going to multiply with the behavior probabilities and divide by them, which means we can write this as an expectation under our behavior policy mu. Which means that if we sample this quantity, we get an unbiased estimate for this quantity that we're actually after, the expected reward under policy pi. So, in short, when following a policy pi, we can use this reweighted sample as an unbiased sample for the expected reward under policy pi. So we're following mu, we can sample according to the policy pi. Note that we're not changing the sampling distribution. So important sampling sometimes refers to actually picking mu in a specific way. Here we're just using the corrections mechanism. So we're using this reweighting of the samples to make sure that the resulting estimates are unbiased samples. And now we can of course apply this to estimating a value function estimate. So we're going to generate some trajectory. We're going to use tau here to refer to this trajectory generated with our behavior policy mu. Now we want to use the return that we generated, because that's all that we have. We have our behavior, we have some return, and the return is a function of the trajectory, so we can write that down quite explicitly. So note here we overload notation slightly by saying g could also be interpreted as a random function of this random trajectory. And specifically the function that it is it just picks out the rewards and adds them together with the appropriate discounting. Now we can use the exact same trick that we just used for the bandit case, for the one-step reward case, and apply this to the Monte Carlo case. And in order to do so, we should have the probability of the trajectory of that full trajectory under our policy pi divided by the probability of the trajectory under our policy mu. This would be the appropriate reweighting in order to get an unbiased estimate of the return under policy pi. For instance, pi could be our greedy policy and mu could be our behavior policy, and we want to estimate the value of the greedy policy. Now this is somewhat of an unwieldy thing, so I've started writing it out here on the slide, so feel free to look at this in a little bit of detail. What is this probability of a trajectory under a policy pi? Well, I didn't maybe make it very explicit in this notation, but the trajectory is meant to start at some state st, right? So first, we're already conditioned on being an st. So the very first step is to consider the probability of the specific action that we've seen, given that state and this policy. We could also additionally consider the probability of being in that state. That doesn't really matter too much. For instance, we could think of this at the beginning of an episode. But for now, let's just consider S to be given, and then we consider probability of selecting action A. This will be different under our target policy than it is for our behavior policy. So we're doing the same process on both sides here. So we're expanding this probability of the trajectory into its components. And then we also consider Given that we now have selected this action, so under the probability of selecting this action, there will be a probability of the reward in the next state that we've seen. And then there will be the probability of selecting the next action, and so on and so on. So the probability of this one trajectory will be maybe somewhat obviously fairly small, because there's a probability of selecting specifically that action, then transitioning specifically to that state, selecting specifically the next action, and so on and so on. This is normal. The probability of a full trajectory will generally be quite small, because the trajectory could be quite long and random. And then we do the exact same thing for the behavior policy as well as we do for the target policy. Now we notice that there are some terms that overlap, and we can cancel those. Particularly, the transition dynamics are the same for both the target policy and the behavior policy. Given that we've selected an action, the probability of then transitioning to the next state matches below and above the dividing bar. That means that the ratio of this subquantity is just 1 anyway, and we can just cancel them out against each other. That means that we're left with this, just the probabilities of selecting the actions. So the probability of selecting the action under that policy, and then the next action under that policy, and so on for both these policies. But these are just by definition the policies themselves. So what we see here is that we get these ratios of policies on every time step, and then we just divide them with each other. So we divide the target policy by the behavior policy. We multiply all of those together, and then we can multiply those with the return, and this will give us an unbiased estimate of the value under pi. It can be a noisy estimate, and again, we do need this condition that the behavior policy will have some probability of selecting all of the actions that the target policy does, because we never want to divide by 0. But if we have that, then we can use this as an estimate. So for instance, if we want to estimate the greedy policy, and we have a uniformly random policy that we're acting with, we could reweight the samples that we get, and then we could use those as an unbiased estimate for our target policy, our greedy policy. In fact, if we consider a greedy target policy, we can see that if any of the actions selected along the way were not greedy, then this total sum would just be 0. Basically, we're just going to ignore returns that don't correspond to the greedy policy in that case. And then additionally, any one where all of the target policies are 1, so in the case where we are considering estimating the greedy policy, the value of the greedy policy, and we have actually found a trajectory where we always select that action corresponding to the greedy policy, then we would upscale this return so that on average, compared to all those zeros that we also accumulate, on average we get an unbiased estimate. So this is a generic technique for off-policy learning. We can generate data under some policy and then evaluate any other policy. Now this might be a bit unwieldy. As I mentioned, for the greedy policy, you would actually have to select all of the actions exactly right in order to learn the value of the greedy policy. And that might not happen that often. A different way to say that is that this is a very high variance estimate. So what do we do when we have high variance? We turn to temporal difference learning. And we can use this to construct temporal difference targets that will also do the same thing. So what we're going to do is we're going to use our temporal difference target, where V is now going to be an estimate of the value of policy pi, so the one that we're interested in. And we're going to reweight this target with importance sampling, but then we only need one step. We only need one ratio of the probability of the target policy divided by the probability of the behavior policy. This, of course, has much lower variance than Monte Carlo importance sampling. This is even more so the case when we're doing importance sampling than it is for the standard difference between OnPolicy temporal difference learning versus Monte Carlo. So this is even maybe more in favor of temporal difference learning than if we do the OnPolicy case. Because we can learn now, even if the policies only match a single step. So whenever you happen to select the greedy action, this TD algorithm can learn about that, can use this to update its value functions. Whereas the Monte Carlo algorithm needed a full trajectory to be greedy, for that special case when we're interested in a greedy target policy. Now let's step through that this is accurate. So we've already done this for the one-step reward case, and we've done it for the more generic case with a generic F. Let's just verify that everything's still fine. So what we're interested in, we have this estimate where we've reweighted it and we've sampled according to this behavior policy mu. And now we're just going to check that everything works out. So we're first going to write out this expectation explicitly. We'll keep the expectation on the inside, which is the expectation given now that we have a state and an action. And we're just expanding that first action. So the expectation we're just expanding in terms of the action selection, which is according to this behavior policy mu. And we're in some state S, so we're just going to replace A and S now with this A that we're summing over and that S that we were conditioning on. This means that V of ST is just VS, and additionally these probabilities are now just for A and S, rather than AT and ST. And then we have the summation on the outside, which is just the probabilities of selecting each of these actions. And then we notice that we can push this summation inside this bracket, so inside the TD error. And this gives us the following, where the mu now cancels with the other mu. And therefore we get a summation over pi of this first bit. And we've also pushed this sum into the minus part, where it remains for now. But then we notice this is just a summation over actions, but the state value doesn't depend on actions. Hence, this summation is just something that sums to 1, and we can replace with anything else that sums to 1. So we will just replace pi here at the end with mu. Because if this is a valid policy, both these sums just sum to 1 and they're multiplied with the state value. So these are exactly equal. Now we know that we have a summation over the probability under the target policy, pi, in both these cases. So we can merge them together again, pull the pi outside of the temporal difference error. And then we notice that we're actually all the way back into a form that we can write as an expectation again. So we do that and we notice that we now have an expectation under policy pi of the unweighted temporal difference error. So feel free to step through this yourself carefully to convince yourself that this is true. So just doing this one correction can give us an unbiased estimate for the temporal difference error under our target policy. Hence, using this for learning means that V would start to approximate V pi. Now that is useful, but we can actually do something interesting, which is a little bit different. We can also consider off-policy learning for action value functions, and interestingly, no importance sampling corrections will be necessary. This is because we are already conditioning on the first action, so we don't need anything to do for that. But on the next step, we can just choose not under the behavior policy, but we can choose under a target policy that we're considering. So the actual action we pick might be under a behavior policy, but we can just bootstrap under the probabilities under the target policy. And that will look like this. So we have our state estimate, state of action value estimate, Q of STAT, and we're going to update that by considering a temporal difference error which takes the first reward and then discounts the next state value under our target policy pi. And then turns out it doesn't matter how we select AT, it doesn't matter how we select AT plus 1, which doesn't even show up in this equation. And we can learn about this target policy for whatever behavior policy we have. Obviously, the same caveat as always applies. If you don't ever actually select certain actions under your behavior policy, you won't actually learn their values. Which means that if you then use them in bootstrapping, these values might be inaccurate. But if your behavior policy is, for instance, some exploratory policy, which does eventually select all of the actions, then we could still learn about a different target policy. So, for instance, again, the target policy could be greedy and the behavior policy could be uniformly at random, and this would still be a valid algorithm. This algorithm is called expected Sarsa in Sesson and Bartow. When expected Sarsa was first introduced in the paper a couple of years ago, well, it was actually first introduced in the first edition of Sesson and Bartow, but it wasn't named. And then in the paper it was called expected Sarsa. That refers to the OnPolicy algorithm, and the more generic version where pi could be any policy is sometimes also called general Q-learning. Because this turns out Q-learning is a special case of this algorithm. But the point here of the expectation is that we don't necessarily have to pick the behavior policy, but we can pick any target policy. However, a special case is when you do pick pi to be equal to your behavior policy mu, you could still do expected Sarsa for OnPolicy learning, and then turns out this update is exactly the same as the Sarsa update, except it has lower variance. So it is unbiased compared to Sarsa, but it has lower variance, and therefore in some sense is strictly preferable to Sarsa. Q-learning happens to be a special case, and we can just consider that by considering pi to be the greedy policy with respect to our action value functions. And if that is the case, then this summation over policies will just basically pick out the max And then we can see this full update becomes exactly Q-learning. So we can see that this algorithm is actually a slightly more general version of Q-learning. Okay, this brings us to the summary of this lecture. Now we're just going to briefly recap basically the whole lecture. And we're going to start with a model-free policy iteration. And recall that the point there was to learn action values to predict the current policy, because that's how policy evaluation works. And policy evaluation is a sub-component of policy iteration. And then we can do the other part, which is policy improvement. For instance, make the policy fully greedy or epsilon greedy. And we talked about how we could extend this idea of policy iteration to be model-free, where both the evaluation step and the improvement step can be done model-free. Then we talked about Q-learning and noted that this is akin to value iteration, where instead of having a separate phase where we maybe evaluate a policy over some time and then make it greedy or improve it, we could also do this in a very tight loop where we immediately make the policy greedy on every step. So when we update our action values, maybe the policy can change immediately. And then Q-learning is a model-free algorithm that is very akin to this value iteration idea. We've also talked about Sarsa and just now about expected Sarsa. And these can be used more similarly to policy iteration, where we could also keep the policy that we're evaluating fixed for a while and on policy estimate that behavior and then do an improvement step. Or we could also immediately update the policy as we go. So Sarsa could also be used online with an epsilon greedy policy, where every time step you're just re-evaluating what are the actions that should be taken. And we talked about the convergence properties of these algorithms as well. But sometimes we're also just interested in maybe estimating a completely different policy. This in general is called OffPolicy Learning, where expected Sarsa could for instance be used to pick any target policy that we're interested in and then trying to learn about the values of that. Learning about the greedy policy is then a special case of OffPolicy Learning, which is the one that is used by Q-learning. In general, we want the behavior and the target policies to improve. That's what it means when we say that we want to do control. And if the target policy is greedy, the behavior policy could still be epsilon greedy or some other type of behavior policy. And then we could construct this target for Q-learning, as we saw earlier, where we just take the first reward. As always, this is a temporal difference method. And then we bootstrap on the state value, which is defined by taking the greedy policy in that state, written out here quite verbosely. And this is equivalent to just considering taking the maximum action value in that state. So conceptually what Q-learning is doing is it's imagining that in the next state it would pick greedily according to its current estimates, and then it's trying to use that as an estimate for the value and backing this up. In Sarsa, similarly but slightly differently, the target and the behavior policies are the same, and we're actually considering the actual action that was taken on the next time step before we update our state action values at time step t. Then, if we want this to converge, because it's an OnPolicy algorithm, we need the additional requirement that the policy becomes greedy. So Q-learning is an off-policy control algorithm that doesn't need this requirement, but Sarsa is on-policy, so for this to actually converge, the policy itself, the behavior itself, should eventually become greedy. One way to do that is to use epsilon greedy or a different type of softmax, which is a generic term referring to algorithms that are not quite greedy, but they're close to greedy. So we're taking a soft maximization of the action values and then using that to infer a policy. And then if you decrease the exploration, you get this property which we call glee, which is greedy in the limits, but it does explore infinitely often if you decay slowly enough. So in summary, Q-learning uses a greedy target policy to learn about. Sarsa uses a stochastic sample from the behavior as a target policy, which means it's on policy because the behavior is used as a target. And in expected Sarsa, we can relax this assumption and we can use any target policy. So both Sarsa and Q-learning can be seen as special cases of expected Sarsa, where for Sarsa the actual sample is stochastic, so the actual policy will be stochastic, and for Q-learning is greedy, but you can pick anything you want. And then we also talked about double learning, where we use a separate value function to evaluate the policy for any policy. Now, double learning is actually not necessary if there's no correlation between the target policy and the value function. Let's say we're doing pure prediction. You could use expected Sarsa, for instance, to learn about a target policy which we're keeping fixed. For instance, you could have a policy that says, what would happen if I always walk forward? Then expected Sarsa could use that to construct a bootstrap target, which would, in the next state, for any transition, in the next state would consider only the action that moves forward. This action wouldn't depend on the action values, and therefore there would be no correlation between selecting the action for the policy and then evaluating it. Then you will not need double learning, there won't be any bias. But of course, in general, there can be correlations, and specifically when using a greedy policy, like in Q-learning, there are quite strong correlations. The whole reason to pick an action is because it has a high value. And then we evaluate that using the same values, and this creates an upward bias. Then double learning can be quite useful. More generally, if there's correlations, double learning can be quite useful, and it can be quite useful to track these action value estimates, just to see whether you might be suffering from overestimations or unrealistic action value estimates. And then if you are, you could consider doing something like double learning to mitigate that bias. That brings us to the end of this lecture. Please continue to use Moodle to ask questions. Thanks everybody who has been asking questions there, and we'll try to always get back to and answering these on a regular basis. And for now, then I want to thank you for your attention, and I'll see you in the next lecture.